Hello everyone, welcome to my class. In today's class, I'm going to start chapter 13, so section 13.1, vector functions and space curves. Let me start the class right away. First, quick overview. In Calculus 1 and Calculus 2, we studied functions in one dimensions. That is, we study the functions from real line to real line. It's a scalar functions. We denoted by y equals to f of x. Now, we will study functions in higher dimensions. That is, our function is going from Rn to Rm, where n and m not necessarily the same. These functions in the higher dimensions take a set of real as an input and returns a vector. In particular, we study following functions. In particular, we study the following types of functions. F from R to Rm, which is called a vector functions. We covered these types of functions in chapter 13. In chapter 14, we cover a function of several variables, where our function is going from Rn to R. And in chapter 16, we cover a functions which goes from Rn to Rm, which is called a vector fields. Quick note, we mostly focus on the cases where both n and m equals 2 and or 3. Let me start now the vector functions. Quick definitions. A vector function is a function denoted by a vector r, whose domain is a set of real numbers and range is a set of vectors, that is multidimensional space. So our vector function is written as vector r, whose domain is r, that means set of reals, and which lands in multidimensional space Rm. So in particular, for m equals to 3, we write vector functions r from set of reals to r cubed, defined by r of t equals to in the vector forms here, ft, gt, ht. These are the component functions of this vector function. And this ft corresponds to the x component, gt corresponds to the y component, and ht corresponds to the g component. So here, ft, gt, and ht are real functions called the component functions of vector functions. Great. Let's move on. Example, vector functions of a straight line through point P, 1, 2, 3, and parallel to a vector V, whose components are 4, 5, 6, is RT equals to 1 plus 4t, 2 plus 5t, 3 plus 6t. So now this is a vector functions. Component are 1 plus 4t, 2 plus 5t, and 3 plus 6t. I hope this definition makes sense to you all. Quick visualization of vector functions. Here domain is R. The vector functions takes the t, means the real numbers, and lands on R cubed. If I pick m equals to 2, then we have the vector functions going from R to R square, then we land in R2 here. Okay, great. Another definitions, the space curve. The endpoints of the vector functions generates a path called a space curve. So now here, each of the tip of these vectors generates a path. This path is called a space curve. Note, the vector functions are vectors, so they obey the rules of vector additions and scalar multiplication. Next, limit and continuity of vector functions. We compute limit component wise as well as continuity component wise. So the definitions: limit of vector functions Rt as t approaches to a is defined as the component y. So limit of the first component, limit of the second component, limit of the third component. If any one of these limit of this component function does not exist, then the limit of our vector function does not exist. Similarly, vector functions Rt is continuous at t equals to a if and only if the limiting value of vector functions at t equals to a equals to the function value of vector functions at a. Next, parametrization of a space curve or functions. One way to do this is to set one of the variables equals a parameter t and rewrite the remaining variables in terms of the parameter t. Example, in one dimensions, the vector function which parameterizes the curve fx equals to e to the x is simply put x equals to t, then y becomes e to the t, so our vector function is then rt equals to vector t comma et. I hope this makes sense to you all. Example 2, in two-dimensional case, the vector functions rt equals to cosine t comma sine t, t between 0 to 2 pi. This parameterizes the unit circle x square plus y square equals to 1. Let's move on. Similarly, in 3 dimensions, the vector functions rt equals to the vector here, the component t cosine t comma t sine t comma t, where t is greater than or equals to 0, parameterizes the circular cone x square plus y square equals to g square, with x is the positive z axis. Now, with this theory concept, let's do some example. First worked example, find the domain of vector functions. The vector function is rt equals to the component here, t square comma radical 9 minus t square comma natural log t plus 1. Or we can write it using ijk, which is I wrote here. So to find the domain of vector functions, now we need to find the domain of each of these component functions and take the intersection of those domain. That will be the domain of our vector functions. Solutions. So here the first component t square is defined for all t. That means the domain of t square is negative infinity to infinite. Second component is radical 9 minus t square. This component function is defined for this 9 minus t square is greater than or equals to 0, which implies t lies between negative 3 and 3. So the interval for or the domain of the second component is t lies between negative 3, including both endpoints. Similarly, the last component functions, natural log of t plus 1, this is defined for t plus 1 strictly greater than 0, which implies t is strictly greater than negative 1. So consequently, the domain is the intersection of negative infinity to infinite, negative 3 to 3, and negative 1, excluding negative 1 to infinite. So our intersection is negative 1 to 3, 3 including, negative 1 excluding. So then this is the domain of our given vector functions. I hope this makes sense to you all. Now let's move on. Example 2, compute the limit. Limit t tends to 1 of rt, where rt is given as t square comma t et comma radical t plus 8. Then we take the limit component y. So let's take this limit of each of these component functions, which I did here. So limit of t square as t goes to 1 is simply 1. And for the second component, limit t goes to 1 of t e minus t becomes simply e to the power minus 1. And the third component of limit t tends to 1 of radical t plus 8 becomes put t equals to 1. So this is 1 plus 8 is 9. Radical 9 is 3. Are we done? Example 3. Compute the limit of these vector functions where rt equals to et minus 1 over t sine t over t 1 over t as t goes to 0. Then let's take the limit of each of the component functions. So the limit of first component functions, limit of e to the t minus 1 over t as t goes to 0, put t equals to 0. So this is e to the 0 is 1 minus 1 is 0 over 0. We have an indeterminate form. Apply the L'Hopital's. To apply the L'Hopital's, we take derivative of numerator and derivative of denominator separately. So the derivative of et minus 1 turns out to be et over derivative of t turns out to be 1. So then put limit t goes to 0. So e to the 0 is 1. So we have 1. And then next, limit t tends to 0 of sine t over t is just 1. We know that the formula in calculus 1. And the third component, limit t tends to 0 of 1 over t is indeterminate form. So then 1 limit doesn't exist means this vector function limit does not exist. I hope this makes sense to you all. Let's move on. Example 4. The vector functions rt, whose components are cosine t, sine t, t, is continuous at t equals to pi, since r at pi equals to all of these component functions, the limit exists as t tends to pi, which is -1, 0, pi. So this function is continuous. Awesome. Great. So far, we have discussed how to find the domain of vector functions and how to compute the limit and continuity of vector functions. Next, let's talk about sketching the vector functions. Example 5. Sketch the curve rt, whose components are cosine t, sine t, and t is greater than or equals to 0. Solution. Here, xt is cosine t, yt is sine t, and zt is t. So let's get rid of t first. So from first two equations, square and add them. This gives us x square plus y square equals to cosine square plus sine square, which is 1. And z is greater than or equals to 0 because z is t is greater than or equals to 0. So that means we have a circle in xy plane, and we are taking all the positive z's. So that means here we start from here and we go toward the positive z by spiral here. We are just going up, up, up. So that means we have a curve confined in the circular cylinder we call the helix. And again, this starts from this point. We can even compute here the values. Put t equals to 0, then cosine 0 is 1, sine 0 is 0, t equals 0 is 0, so 1, 0, 0. So we start at this point here along the x-axis, and then we go up in 2 pi. We make a one rotations there, and then again goes up. That's one idea. Another idea is, let's project. Let's use the projection here. If we project here, project in xy plane, it's a unit circle. If I project in xy plane, then z equals to 0. So this is simply x square plus y square equals to 1, which is a circle. So circular motion in xy plane. Project in yz plane, it's a sine curve, y equals to sine z. Project in yz plane, so x0. So x equals to 0, then y equals to simply sine z. Then that's a sine curve in the yz plane. So its motion is wave motion. Similarly, in xz plane, it's a cosine curve. So think for a second. In the xy plane, it's a circular motion. And in the YZ plane is a wave motion, and in the XZ plane it's also wave motion. Let's combine all of these motions. So that means it's after combining all of these motions, we will get the circular and wave. This is a circular helix. I hope this makes sense to you all. Now let's move on. Example 6. Find a vector function that represents the curve of intersection of cylinder and plane. So here the cylinder is x square plus y square equals to 1. So that means z can take any value. So that means here is x square plus y square equals to 1, this circle, and I can extend this toward the positive z here, as well as negative z, but the plane is here, y plus z equals 2 is here. So all I'm interested in this cylinder and then this plane. So then they intersect at this curve. I extracted this curve here. That's the curve of intersections. So here the projection of the curve of intersection onto xy plane is just a circle. Yeah, if you project this one down on the xy plane, it gives us a circle. Then its parametric equations are x equals to cosine t, y equals to sine t, and t between 0 and 2 pi. So we found the parametric equation for x and y. Let's find for the z. Next, for the z, let's use the equation of the plane. So from the equation of the plane, y plus z equals to 2, z equals to 2 minus y, and y is sine t. So now we have z equals to 2 minus sine t. Then the vector equations is rt equals to cosine t, sine t, 2 minus sine t, t between 0 to 2 pi. So this is the vector equations. If you want to write in parametric form, then we write x t is cosine t, y t is sine t, and z t is 2 minus sine t. So this is the required equations of this intersection curve, which is also called a parametrizations of the curve. I hope this makes sense to you all. Now let's move on. Example 7. Great. Let's do example 7. Find a vector equation for the line segment joining this 2 point P and Q in the space. So let's begin the solutions. Consider the position vector for point P, which is R0, and for point Q, which is R1 vector. Then by formula, the vector equation of the line segment joining PQ is RT equals to 1 minus T times R0 vector plus T times R1 vector, T between 0 and 1. That's the formula we learned in earlier chapter. Then next step, RT equals to 1 minus T, this is the R0 vector, plus T, this is the R1 vector. Then the next step, multiply this vector by 1 minus T, means multiply each of the component by 1 minus T, multiply each of this component in the second vector by T, and then we add the vectors, we add the corresponding components. Then it turns out that vector RT equals to 1 minus 4T, comma 2 plus 3T, comma minus 2 plus 3T, and by the way, T ranges from 0 to 1. I hope this makes sense to you all. So we finish these sections. Thank you.